What's up, everybody? Hope you guys are doing well. Welcome to another day of math with me. So quick story, I got a little brother who's taller than me, and a few summers back he bought a street bike, like a Ninja. Well, I grew up riding dirt bikes and quads and all that good stuff, so obviously I asked if I could ride it. So he let me take it out, I rode it around for a little bit, and I'll tell you, it was awesome. So much fun. I don't know if you ever ridden street bikes or dirt bikes, but make sure you guys do it. Anyways, he did get a little bit of video of me riding it, so short clip, about 3-4 seconds, but I figured I'd let you guys see it, so enjoy. Walker! Alright guys, I hope you like the intro. A few announcements. You guys do have a test this week on Thursday starting at 10 a.m. Again, we're going to go with 2 groups. If you can't make the first testing period, then you can always email me and we'll set you up for the second testing period. For geometry, you guys will be taking your test on chapter 10. You may use one side of a 3x5 inch index card. For algebra 2, you guys are going to be taking your test on chapter 12. You may use both sides of a 3x5 inch index card. If you guys have any questions and would like to review, Wednesday is our review day. So make sure you email me and I'll set up a time where we can somehow figure out a way to probably use Google Hangouts and we can work through any review questions that you guys do have. Again, you guys got to be emailing me if you have questions. I don't know if you do unless you email me. So again, communication is big. Make sure you guys are letting me know if you'd like to review and we can set up a Google Hangouts or anything else that you guys may need. Or I can make a video if you guys want. I can make a video going over certain problems. You guys also have homework that's due at midnight tonight. Instead of being 3 p.m., it's going to be switched to midnight from now on. Last thing I want to go over is homework solutions. I still want you guys to be able to make corrections to the homework that you have. So instead of correcting it in class like we would usually do, I'm just going to email everybody the solutions and you guys can look over it and then make the corrections on your own. Again, let me know if you have questions. All right, enough of me talking. Hope you guys enjoy the lecture. Okay, so today we're looking at section 10.6, geometric probability. Now, personally, I really like probability. It's a really interesting subject. I think it's really useful in everyday life. And personally, I just really like this subject. But today we're looking at geometric probability. But first, let's define what probability is. And to start, we're going to be looking at theoretical probability. So we're going to say that the theoretical probability of an event occurring is the number of outcomes in the event over the total number of outcomes in the sample space. So the way I like to think about it, and whenever we say probability, we're going to say that P for probability of the event. This is what we want to occur. I should write this as, instead of want, I'm going to change this to the event. So the event is what we are looking for to happen, is what we want to occur. The number of outcomes in the event goes on top, over, divided by the total number of events in the total sample space. So an easy way to remember this, the way I like to remember it, is just P, the probability of what you want, is equal to want over total. Want over total. Let's do a quick example of some theoretical probability. And you'll see a lot of this in game theory, like card games or dice games, whatnot, just because in games like that, you really see probability in action. It's a really good way to experiment with all of that. So let's say that we take a deck of cards, and for those of you who know, there are 52 cards in a deck. We have 4 suits. The 4 suits we have, it's a terrible spade. We have spades, we have clovers, and then we have our diamonds, and then we also have the hearts. So these are the 4 suits in a deck of cards. Now there's 13 diamonds, 13 hearts. So there's 26 of the diamonds and hearts, and there are 26 spades and clovers. So let's say that I want to find the probability of the event. Let's say I take a deck of cards and I randomly pull one out of the deck. I'm looking for a red card to be pulled out of the deck. If I shuffle them, randomly pull one out. Well, this will be equal. So we're looking for red. That's the event, right? That's our event. That's what we want to occur. So how many red cards do I have in the deck? Well, I have 26. So that's the number that I want to happen. That's the number of outcomes in the event. So the 26 goes on top. That's what I want to occur. That's the total number of outcomes. Well, how many do I have total? What's the total number of outcomes in the sample space? Well, I have 52 total cards in the deck. So this would be my probability, which reduces to 1/2. So the probability that a red card would be pulled is 1/2. That'd be my answer. Now the chance that a red card would be pulled, so chance, would be 50%. So chances in percentage, probability we're going to keep in a fraction or decimal. And chapter 13, we're going to be looking at probability more specifically. It gets pretty interesting, but we'll worry about all the details then. Today, while we're looking at probability, is because we also have what's called geometric probability. So the geometric probability of an event occurring is found by determining a ratio of geometric measures such as length or area. Geometric probability is used when the experiment has an infinite number of outcomes. So the reason we have infinite is because you take your area, there's an infinite number of points in there, and that's why we can create that ratio of length or area and find the probability of an event occurring. So let's go and look at a few examples. So let's look at this section here first. So let's say that I wanted to take this line segment AD. Here's my line segment. And so the probability of the event is equal to what we want over the total. So another way that I could write this is P of E is equal to the event over the sample space. So when I look down here to my first example, I have my sample space, and that is the total number possible. What's my total possible outcomes? Well, the total possible is everything on this line segment. So all the points on line segment AD is my sample space. That's the total possible outcomes. Well, what do I want to happen? What's the event that I'm looking for? The event that I'm looking for in this case, this is what I want. What do I want to happen? Let's say that I'm looking for only points to be taken or to land on line segment BC, right there. All the points on line segment BC. So basically the picture you can think of is that I take this line segment, and if I randomly select a point on that line segment, what's the probability that it would fall on line segment BC out of the total segment AD? So picture just randomly selecting a point. What's the probability to land on BC? Well, to do this, all I'm going to do is say the probability of the event BC is going to be equal to what we want to occur, so number of points on BC, over the total, which is the sample space 80. And then you would have actual measurements there, and we could calculate the probability. Now let's go and look at the angle measure here. So for the angle measure, we have our a circle here. We have the sector of the circle right there. And let's say that that's a dartboard. A little example. Let's say that's a dartboard, and I want to find the probability if I close my eyes and throw the dart at this dartboard here. What's the probability that it will land on this shaded region? That's kind of the picture that we're looking at. So what's my sample space? What's my total? Well, the total is all the points in the circle. Everything. That's my sample space. That's the total. What do I want to occur? Well, I want to be on the shaded region here. So what I want, the event that I'm looking for, is all the points in the shaded region. Well, how would I calculate this? So this was actually kind of interesting, because if I take the probability, what we're going to do is calculate the area. I calculate the area of the shaded region. That's what I want to occur. That's going to go on top, right? On top up here. And then the total is going to be the area of the entire circle. So I do shaded region area over the total area circle. Well, how do I calculate the area of the shaded region right here? Well, if I take the entire area, to calculate the area of the entire circle, I'll write this a little bit bigger. That's going to be pi times the radius squared. That will give me all of this area. But I only want this little section here. So how do I get this section? Well, I know that in a circle, there's a total of 360 degrees, and I only want x degrees. I only want a portion of it. So to get this little portion, what I'm going to do is take x over 360. So if I take x over 360, multiply it to the total area, that will give me that shaded region. It's only going to be that portion of the entire circle. Well, that's what I want to occur. That's the event that I'm looking for. What's my total? Well, the total is pi radius squared. That gives me the area of the entire circle. Well, hopefully you see that these cancel out. I'm just left with x over 360. So to calculate the area, or to calculate the probability of an angle measure on this circle here, all I have to do is say that the probability of the event is just equal to x over 360, where x is just the given angle measurement here. The angle measurement of the shaded region. And that's how you calculate that probability. Let's do one more. Let's say that I want to calculate the probability that, similar scenario here, I'm still looking for the probability that the randomly selected point is in the shaded region. So it's the same scenario, except we have non-circle shapes. So what's my sample space? What's the total possible outcomes? The total possible outcomes is all the points in the rectangle, right? Because that's my total space. Now what do I want to occur? I want the shaded region. So the event that I'm looking for, I want all points in the triangle. To calculate this probability, I'm going to say that the probability is equal to the area of the triangle over the area of the rectangle. And if I calculate both those areas, create that ratio, that will give me the probability of the randomly selected point landing or being taken from the shaded region and not the non-shaded region. Let's do a few examples based off those previous things we just went over. So our first example here is what's the probability that a point chosen at random on our line segment XZ is on the segment XY. So to do this, I'm going to, just a second, erase this. Remember, again, it's probability of the event is equal to want over total. Event over sample space. So what do I want to occur? I want the point to be on XY. So here is XY. That has 5 units, so P of XY is equal to 5 over the total. What's the total? Total length is 14. So that would be my answer. I could convert this to a decimal. That would convert to 0.3, approximately 357. Now don't put it into percentage because percentage is chance, and I'm not looking for chance, so keep it as a fraction or a decimal. All right, next question. Let's find the probability that the pointer does not. Now this is really important how it says does not. So the pointer does not land on white. So if I don't want it to land on this white section here, then I'm going to be looking for everything but white. So the way that I could do this, there's 2 ways I could do it. I'll show you the easy method, I guess. The probability of not white is, let's just add up all these individual angles here. When I add up 30 plus a 45 plus 135 and 90, that gives me a total of 300. And the total sample space is, for the circle, is 360. So I do what I want is 300 over the total 360. So that reduces to 5/6. Now I could also go like this. This way is perfectly fine, but I could also go like this. I could do 1 minus the white, which is the same thing as 360 over 360 minus 60 over 360. And the reason I'm doing 1 minus that is because it basically just gets rid of that white section. So that gives me 300 over 360, which reduces to 5/6 like previously calculated. There's 2 ways I could do it. You just have to pay attention to what you're actually asked to solve for. So if I were to ask for you to solve for what's the probability it lands on this section here, well, it's 90, so you do 90 over 360 and then reduce. Okay, let's do one more. Find the probability that a point chosen randomly inside the rectangle, so that's your total, is in the square. So I want my randomly selected point to be in the square, and my total space, my sample space, is the rectangle. So what we're going to do is calculate the area of the square and do that area divided by, make a ratio, over the total rectangle area. So let's calculate each of these individually. So the area of the rectangle is base times height, 25 times 10. Gives me 250, and that's centimeters squared. And then what's the area of the square? Well, one side length is 5, so I do 5 squared. It gives me 25 centimeters squared. So the probability that the randomly selected point lands in the square is equal to 25, because that's what I want. I want the square, over 250 centimeters squared. That's my total sample space. Well, my units cancel. 25 divided by 250 is equal to 1 over 10. So that would be my solution. So if I randomly selected a point within that whole rectangle, the likelihood that it would land within the square would be 1 out of 10, or 0.1. The chance that would happen is 10%, but again, we're looking at probability, which is a fraction or a decimal. Alright guys, so that's it for our lecture today. Email me if you have any questions. Again, we do have our test this Thursday at 10 a.m. The first group will be testing at 10 a.m. Tomorrow, we're just going to have a review session, so if you guys need help, let me know, and we'll get that figured out. Alright, have a good day.